When we walk, ground friction acts on our foot. Work done by friction is positive, negative or 0. That is the question that we want to understand in this video. I welcome you all on this channel of mine. So, here is today's discussion. When you are walking, there is a friction force acting on your foot. Now, usually when you walk in a very normal fashion, your shoes don't rub the ground. The contact point of the shoe with the ground is actually not moving. Your leg muscle tries to push your foot in backward direction. The muscle force is trying to push your foot in backward direction. So, this particular point, the toe that is touching the ground, is having a tendency to move backward. If the surface is slippery, means there is no friction, then what will happen? If you apply muscle force on your toe and try to push it in backward direction, this toe is going to slide backward and you will fall. Most likely you will fall. So, normally we don't encounter such surfaces where there is no friction. Normally our ground does offer good amount of friction to our shoes. So, when our muscle force, leg muscle, pushes the toe in backward direction, this point has a tendency to slide backward, and friction always opposes rubbing. It always opposes rubbing between two surfaces, relative motion between two surfaces. So, immediately the friction force will take this direction. What is happening? Friction has got nothing to do with motion of this point. Friction has got nothing to do with the fact where your whole body is going. Friction has got nothing to do with this point, this point, this point or this point. Motion of these points are no concern for friction. Friction is only bothered about motion of this point that is touching the ground. And when you apply muscle force, this point has a tendency to go backward. Friction will try to prevent that rubbing and it will take a forward direction. And this is the external force which accelerates you. That means your velocity becomes 0 to 5 meters per second in some amount of time if you start running. So, this is the friction force, external force, which is responsible for accelerating your body. But does this friction work? Does this friction perform work? Answer is very obvious, no. Why? Because this contact point is not moving actually. Your whole body is moving, but this contact point is not moving. This foot is resting on ground and the other foot, this foot is resting on ground and the other foot is not on ground. It is lifted up from the ground. Now, when this foot will come to ground, this foot will get lifted up. So, friction force right now is acting here on this foot, but this particular point is not moving, it is not sliding. The whole body is moving, but this point is not moving. You are moving in this fashion. The toe that is resting on ground is not sliding. The next moment this toe comes to ground, it is not rubbing the ground. The next moment this toe comes to ground, it is not rubbing the ground. Next moment this toe comes to ground, it is not rubbing the ground. Next moment this toe goes to ground. So, the point of contact is not sliding. Friction force is acting here and this particular thing is not moving. The point of application of force is not moving. Therefore, this friction does not perform any work. This friction does not perform any work. Now, you may be amazed. If we apply work energy theorem on our body, friction force is not performing work, but our kinetic energy increases. Suppose I am at rest and now I start running. So, kinetic energy of my body has increased substantially from 0, it has become 500 joule or 800 joule. Now, where from this kinetic energy comes? Work energy theorem says that work done by all forces on a system is change in kinetic energy. If friction force is not performing work on me, then who is performing work on me? That is the great question that comes to our mind. You can pause the video and think over it. The fact is, our internal muscle forces do work. Yes, in work energy theorem, there is no differentiation between external and internal forces. The theorem simply says work done by all forces is equal to change in kinetic energy. So, work done by internal forces can also change the kinetic energy of a system. So here the muscle forces are performing work in moving the joints, etc., and that causes the change in kinetic energy of our body. So yes, internal forces are causing change in kinetic energy of the body. But if you try to explain this situation from the point of view of Newton's laws of motion, Newton's laws of motion says that only external force can cause acceleration. So this friction is the external force which is responsible for accelerating our body. Yes, in terms of Newton's law, but when you try to explain the situation in terms of work energy theorem, it is the internal muscle forces which are performing work which changes the kinetic energy of your body. Now, there is another question which you can answer from this one. It is often said that when the surface is slippery, you should take small steps while walking. Yes, why? Taking bigger strides, bigger steps simply means the situation is more or less like this. Your muscle, leg muscle is trying to push this foot in backward direction with a great force. And if you are applying a great force trying to push this foot backward and friction is not sufficient, then this point is going to move backward. That means it will slip. But if you take, if you take very small steps, then in that case, when you walk with small steps, then this is the situation more or less. That means your leg muscles are not applying a great force in backward direction. Therefore, even a small friction will not allow this point to slide, because the backward force that muscle is applying on toe can be balanced by the friction force acting here. If the surface is slippery, then also there is some friction, and it is sufficient to balance the backward force applied by your muscle on the toe, and it will not allow this point to slip. So whenever you are walking on a slippery surface, make sure that you take small steps. If you take longer strides, you are going to fall. And the situation is very similar for a moving car or moving bike. This is the wheel resting on ground. Suppose this is wheel of a car or a bike. Now what happens when you start the engine, engage the gearbox? There is a torque, there is a twist. The engine tries to rotate this shaft attached to the wheel, and because of this torque, because of this rotation, what happens? This point has a tendency to move backward, just like your leg muscle is pushing this point backward. Similarly, when you engage the gearbox, this wheel experiences a torque, and that torque is trying to move this point in backward direction. It is very similar mechanism. So when this point wants to go back, the ground friction will immediately act in forward direction, and it will try its best to prevent this point from sliding on the ground. The friction, as far as possible, will not allow any rubbing, and that is what happens when wheel performs rolling without sliding, pure rolling motion. This contact point is never allowed to slide, and whole wheel is moving, whole car is moving, but this particular point, the point which is in contact with the ground, never moves. In this case also, the friction force that is acting here will not perform any work, because the point of contact, the point where the friction is acting, the point of application of friction force is not moving. Its velocity is 0. So instantaneous power of friction force obviously is 0. Now when this wheel tries to climb up an incline, it is moving like this, it is rolling, let us say. Then what happens? I guess most of you know that if you place some object on an inclined surface and there is no friction, there is a mg sin theta force, there is a component of weight in this direction which will try to retard this. If the wheel is climbing up, there is a force that is trying to retard this. Now what does that mean? It means if there is no friction, then this motion, translational motion of wheel, is going to get retarded, isn't it? Because of that component of weight acting in this direction. So if the velocity decreases, then this point again has a tendency to slide, because the rotation is fast. There is nobody who can actually decrease the rotation. If you roll a wheel on the incline and leave it and assume that there is no friction, there is no torque which is going to reduce this rotation. So, rotation remains fast, but this force component of weight decreases velocity. So, what happens very soon, this rotation will become very fast and this point of contact will again start to move in backward direction. If there is friction present, it will never allow this to happen, and therefore, mind you students, many of you might be having this confusion or you might be making such mistakes while solving questions. If a wheel is climbing up, it is rolling, friction force is not acting in downward direction, it is acting this way only. Yes, friction is acting this way only. This component of weight is there to decrease the velocity, but to decrease the omega, angular speed, there has to be a torque in this direction. Friction provides that torque. If there is no friction, then soon this point will start rubbing the inclined plane. This point will be moving backward, and friction does not like that. So, it will try its level best to not allow that point to slide, and that is why friction will take a direction this way. Again, if the motion is pure rolling, that means this point is not sliding. So, contact point is not sliding. Friction force is acting on a point which is instantaneously at rest. Friction again performs no work. Thank you for watching this video. I hope at least few of your concepts got cleared in this very short video. Keep watching and do subscribe to this channel if you haven't till now. Goodbye.